Okay, finally. Today I'm going to talk to you about the research stay I've been doing in Germany at the Helmholtz-Zentrum Dresden-Rossendorf, which is located in Dresden. I didn't prepare much of an introduction of things. I'm just like straight. It's not working. Okay, this is not working. Okay, the goal of the research stay is to determine the droplet size distribution of annular flows. Annular flows, as you might know, is a flow regime of two-phase flows. For instance, when we have a gas phase and a liquid phase flowing together in the pipe, and when the amount of gas is very high, we have this regime where the liquid goes to the walls of the pipe, and in the center, in the core of the pipe, we have a strong flow of gas. And of course, there are a lot of droplet detrainment into the gas core and in the backwards direction. This is not working. Sí, no, hoy la probé, ahí. So, this is the experimental facility they have there. Here is a 14 millimeters plexiglass pipe. And they have, okay, the air, and for the water they have some nozzles to put it already in the shape of drops. And for measuring the droplet size distribution, they develop this port over here where the flow goes in like through the screen here, and we have these two little pipes like to penetrate the film, the liquid film, so we can measure with a camera here. No? So this is the flow, these are the two little pipes. We put a light source here and the camera, so we can record what's going on, record the drops. Because if we want to look what's going on from outside, we just see the liquid film, and it's impossible to distinguish the drops inside. So, when I arrived, I didn't do the measurements. They already made the measurements and they want me to process them. So they give me a lot of images from a straight pipe, a pipe with an orifice, like a contraction and then an expansion. And they made measurements at 3 axial positions for the straight pipe, 3 axial positions for the orifice, and 4 axial positions for the expansion. These letters B, C, D stands for different axial positions. And these are some examples of the images they have. No? So let's say the flow goes from left to right, and we catch, the drops are catch there. And for instance, in 2 consecutive images, there's no repeated drops. I mean, it's not like a continuous video. The frame rate is quite low, so they don't want to measure like velocity, they just want droplet size distribution. So we see that there are very different topologies on the flow inside, and I'm going to talk a little bit more about this in the results section. So, for getting the droplet size distribution, I use the scikit-image and scipy packages for Python. And the first instance was, okay, to make a mask and reshape, because you know the images that look like this. Okay, I don't have the images. They have a small area, a region of interest, let's say. So an ellipse was made to identify them. Then very dark images are discarded. Now here we have the amount of images and the mean intensity in the image. If it is very dark, we have a very low point here, and it's mostly all black in the image. So these images are discarded because they don't give any information. So we set a threshold. Then we pick also some of the most bright images and calculate a mean. So we get like a background image, because they didn't provide me with background images. That sometimes it's good practice to take an image without any flow, let's say only gas, and see how's the lighting, because the lighting never is completely even in the. Then, well, dividing each frame by the mean image and making a stretch of the histogram, we get from a raw image like this, with this histogram, with low gradients between the drops and the background, to some image like this, where the background is white, is close to 255. So these are all the pixels belonging to the background, and these are mostly the pixels belonging to the drops. And there's much contrast, it's much easy to identify the drops there. Now, to identify these objects, the first technique applied was an edge detection technique with the Canny filter. I get here a single drop, for example, to show you the step by step. So the first step is a noise reduction, applying a Gaussian filter, and we get something like this. The Gaussian filter is just step on a pixel and calculate the mean with all the neighbors, and we get something like this, much more smoother. We see that there's not much noise from the background here, it's much whiter, much even. Then we apply a gradient calculation. For this, the procedure for the Canny filter is to apply an horizontal gradient. Now here we apply this kernel, we convolve this in the whole image. We apply both the horizontal one and the vertical one. No? We just have to overlap this matrix in every pixel here and apply. If we overlap this in a pixel, we multiply this pixel for -1, this for -2, this for -1, for 0, and we add up all together here in this point. So here we identify the horizontal gradient, right? If there's a gradient in this direction, so we would get vertical lines. And the same for the vertical derivative. And this is very small. So here we calculate an image I sub x and I sub y, and applying the quadratic mean, we get this image like this. So now we identified like the edges of these things. Now we apply a non-maximum suppression, because we want the edges, we want it to be 1 pixel width. But here we keep the value of the gradient, right? This is not black or white. I don't know if you can notice, this is slightly gray, and there might be some very close to dark around here. So now we apply the double threshold. For this, you can set 2 thresholds. That those are inputs of the filter, and now, yes, we got only black and white, a binary image. What the double threshold do is, okay, first, sorry, to pass from here to here, it searches for every pixel if there's a higher gradient in the neighbors, and keeps only the maximum. So it's non-maximum suppression. All what is not maximum is suppressed, and we get this. And now it searches if there are 2 thresholds. If you get the higher threshold, it's like a big gradient, you keep it. And if it's in the middle, it looks, okay, we have a neighbor strong, yes, then I'm strong too. If I am over here alone and I'm in the middle of the two thresholds, okay, you are out, you are black. So in the end we get all these edges. So once applied the Canny filter, you might get a perfect close edge, but sometimes the gradient is not enough somewhere and you get something like this. And if you apply just a filling closed regions, this would never be closed, and in the end you would discard them. So first we apply a closed contours with you can set, okay, if there's a neighbor 3 pixels away, you can count it as a neighbor and that. So then we apply the closing and the filling. And in the end we get this, okay, we say this is a binary image where black is background and white is the object we want to identify. So here I have an example with 2 sets of thresholds for the Canny edge detector. So this is a little bit more strict because we need 150 here and the high threshold here is 90. So if you apply all the process, we see that here there are more droplets identified. For instance, this one that seems to be with good contrast. Apparently it's not possible to make a closed contour and it's not identified, but here it is. So these are some of the tuning parameters. More about tuning parameters. This is another example, no? Well, now it's normalized, the thresholds from 0 to 1. This is a very restrictive threshold. Only one drop has been detected. With very flexible threshold, we got a lot of them, but for example, this one is very out of focus, so when a drop is out of focus, it might get distorted the real shape, so you will not measure what you want to measure. So in the end, you want to discard these kind of things. So the idea was to, okay, select low thresholds, but then apply some more parameters. For example, looking at the eccentricity of the objects. For instance, if we get like a filament, that sometimes we have them, it's not a drop, so the eccentricity we say this is not a drop. The solidity, the same if it's with a lot of concave stuffs, and also the mean intensity, which is this example. Here it would be a drop detected, but here you say no, look, this is not enough intensity. It's too bright to be a drop. Okay, so once we apply all these, we get these identified drops, and we want now to measure the size of them to characterize the size distribution. For this, we apply the equivalent sphere diameter from Siegenheim, where the first thing to do is to identify the long axis of the drop. Then we determine the minor axis as the one that is perpendicular to it and the longest possible, and also the closest to the centroid. This is the centroid of the particle. Then we divide the object in two with the minor axis. Again, we have these two centroids for the two halves of the drop. Then we calculate this distance, and then we rotate each half 180 degrees or p degrees, and we add them up, and we said that this is the volume of the drop. And then, as is equivalent to a sphere, we apply the equation of the diameter of a sphere, and we get the size, the characterized size of the drop. But of course, this is measured in pixels. So for the calibration of the pixels, they give me pictures of this target image, where each bar is, of course, of a known size and that. And we have, for instance, the group 0 and elements 1, 2, 3, 4, 5, 6. Then we have group 1 with elements 1, 2, 3, 4, 5, 6. Group 2 with elements 1, 2, 3, 4, 5. And there's until group 7, which are very, very small there inside. So this is, for instance, an image of group 2, element 3. So I applied the same algorithm I was applying to the drops and calculate how many pixels are in this known size. So I calculate the size of the pixels like this. Oops, there. So it's about 5 micrometers in size 1 pixel. So then we apply also some validation. These are images of particles of 50 micrometers each. So I applied again the same algorithm and get this distribution. You see the mean is 51 with a deviation of 6. The provider of the particles didn't provide us with a distribution of the particles. They just said these are 50 micrometers. I guess there must be some deviation, but there was not, like, to compare. But anyway, the result seems to be quite good, very close to 50 micrometers. The standard deviation is not that big. It's a narrow curve. And now some results of the drops. So these are results for a straight pipe. This is the scheme that they were using. This TG14 it's an acronym in German for the measurement port of the droplets, that it's located here at the axial position B that I was telling at the beginning. Then it's located here and then here. It's like to analyze the development of the flow. No? And this is a typical distribution of the droplet size. No? The droplet size are supposed to be distributed log normally. So this is a log normal distribution. This is the equation of a log normal distribution in the standard way. You can find it everywhere. And if we try to do a fitting of this equation into this histogram, we get the squares here. No? It's like not very logarithmic, one could say. But if you apply a shifted log normal, applying this parameter delta here, we get this triangle one, and it fits quite well. Also, something very important is that we cut, with this algorithm and this processing, we catch this cascade here. Because, as I told you, the 1 pixel is 5 micrometers in size, so we cannot measure something smaller than 25 diameters, 25 pixels in diameter, because we won't be able to have a gradient, right? Of course, when we got 1 pixel elements identified, it's discarded as noise, because if done, it would be a completely mess. But now I want to show you the same results, but now instead of applying the size distribution, I applied the volume distribution, which is applied the same histogram, but using weights in the histogram with the volume of the drops. And now, applying the standard log normal distribution, we get a way better fitting without the shifting, this delta parameter. So, and it's already proven that the drops are distributed with a log normal distribution in volume. So this it's nice to have these results here. So I can show you a lot of distributions like this, but they won't tell you anything because they are very similar, each one. So now I want to show you some of the actual development. No? This is for a straight pipe. And these are the results from the image processing analysis. No? I told you that we have 3 axial positions that they will call B, C, and D. This is the nomenclature they have. I wanted to keep it because if not, I would get really messy with the names later if I start changing them. So position B is at 4.6 diameter from the nozzles, from the mixing chamber of the 2 phases, let's say. And we get 4,000 and 5,000 images in total, drops identified by the algorithm. And what we got here, this is a tomography, an X-ray tomography of the pipe, of the same flow. And we see that there's a slight deviation at the beginning. I assume this is because of the mixing chamber. The last nozzle was applying this direction, so it makes like a deviation. Also at the beginning there's only drops, there's no film, because the drops are injected with the nozzles as drops. And then the film starts to get thicker. This is a tomography, so what you get, these colors are the thickness of the film, the water film. So what I was telling you, that at the beginning there's no much film, is almost blue, and we get a maximum value of the film here, and then we could say that from 25 diameters the film is developed. No? It's pretty much the same. And the positions B, C, and D are these ones here. So this is the total number of droplets identified, the total volume of these droplets, and the mean diameter of these drops. So we can see that at the beginning in B we have very small droplets because they are produced by the nozzles. We have an imbalance. No? There are 3 colors for each position: alpha, beta, and gamma. These are the focus plane. And what it means is the focus plane beta is in the middle of the pipe, let's say in the middle. The focus plane alpha is a little bit displaced towards, let's say if this is direction, towards the left of the pipe, all in the same vertical position, but displaced in here. So there's an imbalance in the population of the drops towards alpha. Alpha is towards up here. So we see here that there's much thicker film in this direction than in this direction of the pipe. So this seems to be in concordance with the tomography that they give me. Then when we go to position C, we see the imbalance in the other direction. We also see much more or less droplets. And why is this? Because here the thickness of the film is on its peak almost. So the fraction of liquid in the film is bigger than the fraction of liquid in the drops. This means that drops from here start forming the film, right? So we have less volume of water in drops and more in the film. And finally, D is a developed flow, so we have a more even distribution. The volume is somehow in the middle, stable, and the mean diameters seem to be 80 micrometers. Right. So it seems to be in concordance, the results from the drops and the image processing and the results from the tomography that they perform. Now, these are the results for the actual development in the pipe with an orifice. We have Again, 3 axial positions. Now in the zone of developed flows, this is more than 100 diameters from the mixing chamber. And we see that at position B, this is very similar to a developed flow, as I showed you in the previous one here. Even very close to 40,000, sorry, 80 micrometers in mean diameter, which is very close here, 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 and here, position B. Then we see a big reduction at C. So I have some examples of images. This is at position B. Here, this is a developed flow. This is at position C, 3 different examples, right? This is just 1 diameter from the orifice. One would say, okay, but if we have an orifice, we have the liquid film has to come into the orifice and we will have more drops. Well, we have more structures, but not particularly drops. No? We have these shapes like this. And of course, we have much more fraction of the liquid in the core of the pipe and not as liquid film, but they are not particularly drops. So they are not identified as drops. We have almost half of the drops. And then we see a big amount, increase in the amount of drops, because when these big structures that are heavier and start making the film again, and also they break and stuff, and so we have much more drops here. Okay, and finally, these are the results for the expansion. We have something similar than in the orifice. Like a developed flow here, there are some peaks here that I don't finish to understand yet. Then we have this reduction and the increase again. The expansion is here. So B is very close, is a developed flow. C is also 1.1 diameter after the expansion. We have same phenomena, then a big increase, and then this. I was expecting to be like a developed flow, but I had some imbalance again in the population that I still have to think what's going on there. So, as a summary, 3 elements were processed during the research stage. In total, 10 axial positions with almost 80,000 images were processed. The initial cascade was there, so this says that the small droplets are identified. There are very different topologies, and this makes very difficult to use a global algorithm with the same parameters. And as I am comparing the amount of drops detected, it's needed to use the same parameters with the same algorithm. If not, it won't say nothing if for one axial position I have 40,000 droplets detected, and in other one I have 60. Maybe it's because you use different tuning parameters, right? And the result seems to be consistent with other techniques and the observations. So in general, we were happy with the results, and we are aiming to publicate them now. And that's it. If you have any questions. Yes.
So you still can detect these filaments, right?
You can detect them, but they are really tricky, because usually these filaments are so big and they are not only in the focus plane and develop like a plane thing. So as they have this dimension too. And this provokes this, you see there's no much gradient here. There's very smooth, so it's really tricky to get them properly, because they start to merge all together. If you want to be able to detect this edge with a very low gradient, you also will detect this one, and in the end you get all together, but it's not really together, for example. Yeah.
It seems that in this case, having an orifice somehow ensures a really constant diameter for the droplets, right? So both of B, C, and D, so this orifice looks like not doing much to the diameter, right?
To the diameter, not particularly. Yeah, we can see that they are mostly like this is the mean, right? There are other